So let's go ahead and talk a little bit about Chapter 6. First topic in Chapter 6. Now, Chapter 6 really is actually just going to be more Chapter 5 stuff, just introducing more forces. First topic for Chapter 6 is going to be friction. So we want to talk about friction. And classic example of friction here is that you have an object, it's sitting here, you push on it, and even though you're pushing on it, it doesn't move until you push really hard on it. And so you've got to push a certain amount before it starts moving. Likewise, when you set something on an incline, and so I often do this as a demo in class, is I'll have an inclined plane and I'll just set something on it and it doesn't slide down. And so that would be an example of friction. And so that would be friction, but so sometimes it'll slide, sometimes it doesn't. If it doesn't slide, then friction is holding it there. And so now, one of the things we discover is if something is sliding, the friction is different than if it's not sliding. In other words, if it's just sitting there, that's what we call static friction. And if it's sliding, that is what we call kinetic friction. So I'm going to actually introduce these two slightly differently. First of all, with static friction, then what's happening is I push a little bit. So this object might, have 14 kilograms of mass, and I push on it with a Newton, nothing happens. Push at 2 newtons, nothing happens. 2.5 newtons, nothing happens. 2.6 newtons, nothing happens. So nothing's happening until I get 2.7 newtons and it starts sliding. And so that means that there's friction that resists this. Now with the friction is if I exert a force to the right, the friction has to be opposed to that. And so what we do typically is, and what your book does, is it uses lowercase f to represent friction. Now in this case, the example that I just gave you right here, then what happens was that I had to exert a certain amount of force until it started to move. Now, one of the things we discover is that if this object had been 28 kilograms, then experimentally, what I would find is that if this was 28 kilograms, 1 newton didn't make it move, 2 didn't make it move, 3 didn't make it move, 4 didn't make it move, 5 did not make it move, 5.1 did not make it move, 5.2 did not, but 5.3 it moved. Okay. And so if I double the mass, then I double the amount of force it takes to make it move. Okay. Well, if I push down on it harder, it also, so in other words, if I push down on it, that would also increase the amount of force I would have in order to make it go. So the key is the normal force. Now why is that a big? Well, if this thing is sitting here, okay, then what's happening is, at the microscopic level, if you zoom in here, then surfaces, even they look smooth, they aren't smooth. And so what happens is that these bumps and ridges sort of engage with each other, and you have to shove past them. And you really actually, what happens is sometimes you break them off, sometimes that you get spot interactions here, bonds, and you have to pull atoms and things loose to make things move. Okay, so literally when you start sliding surfaces past each other, then you're damaging the surface in the sense that you're scraping bits and pieces of it all. Now, sometimes that's what you want. Sometimes you want this friction to do something. For example, sandpaper. You want to have lots of friction so that it actually does something to what you're doing. A scouring pad, to clean pots and pans and things. You want it to have lots of friction. You don't want to just slide past the food stuck on the pan. You want to scrape it off. And so these are examples. You want a bunch of friction. The other thing is sometimes you want a bunch of friction. For example, your tires, you want to have friction between the tires and the road, otherwise they slip and they slide. You want friction between your shoes and the road, on the ground. Otherwise, when you try to take a step, then it slides. And so you want to have friction sometimes. And so, but that motion does that friction does damage surfaces. So your shoes, the soles of your shoes show wear over time. Your tires show wear over time. And so those are cases here where the friction is beneficial, but it does wear down the surfaces. Again, friction between the brake pads and the brake discs. That friction is what stops a car, and so it's good to have that friction in there. If you were like lubricate the brakes, the car wouldn't stop. That is, lubricate the pads. Then the car doesn't stop. And so until you scrape off all the lubrication. But again, it wears down the brake parts, and so so friction does damage the surface. Now, back to the example here of static friction. Then what I saw was that if I doubled the mass, that doubles the normal force. And so it's the frictional force is going to be proportionate to the normal force. Okay, and we call this proportionality, lowercase Greek mu, the coefficient of friction. So coefficient of static friction here. Now, really, this is an inequality, because the frictional force, if I exert a force here, the frictional force resists that. The frictional force for static friction is only as big as it needs to be. In other words, if I do not exert a force, the static friction is zero. Okay, so the static friction is not a set number. The static friction is whatever it needs to be to keep it from moving, and the biggest it can be is mu sub s times n. Okay, now what is mu sub s? Mu sub s is the coefficient of static friction. Okay, and it's unitless. Okay, it's the coefficient of friction, so it's unitless. All it is a number. So if mu sub s is 0.25, that means that the frictional force, the biggest it can be, is 25% of the normal force. If it's equal to 0.5, then the biggest that it can be is half the normal force. Okay, so that's your introduction to static friction. Well, again, if I have an object on an incline, it sometimes doesn't slide down, because, I mean, you can do this, put inclined object slightly inclined and put something on it. It will sometimes just sit there because static friction is resisting the motion. So we have mg down like that. We have the normal force like that. And so we have static friction right here. And so we know that the force down the incline is going to be mg sine theta. Resisting that is static friction, so that's going to be ma. Well, if a is 0, then that means that fs is mg cosine theta. Now, the biggest that fs can be, so fs max, the biggest it can be, is mu sub s times the normal. Well, the normal is going to be mg cosine theta. So we could then say that mg, okay, so mu times mg cosine theta equals m sine theta. This is the maximum condition right here. Okay, So normally it's going to be less, and but this is the max it can be. So you notice what happens as the angle gets bigger here, then the cosine gets smaller and the sine gets bigger. So there is a maximum angle. When the sine's really small, then it's easy because friction's going to be mg sine theta. And so this is the static friction. This is the max it can be up here. And so what happens is that as the angle gets bigger, the friction gets bigger until it reaches that point. That allows us to calculate the maximum angle. So mu mg cosine theta max equals mg sine theta max. Well, the m's cancel, the g's cancel, so mu is going to be the sine over cosine, so tangent theta max. Okay, so if you happen to know the coefficient of static friction here, then you could figure out the maximum angle. So the maximum angle would be equal to the inverse tangent of mu sub s. Okay, so that means that you ought to be able to figure it out. In other words, if mu sub s happens to be 0.2, okay, then what you find is that the maximum angle is only about 11.3 degrees. Okay, if mu sub s is going to be equal to 3.355, then theta max is going to be 19.5 degrees. If mu sub s is going to be 0.650, then what you find is that theta max is going to be equal to 33.0 degrees. Okay, so in other words, this determines. Now, what determines this? Well, because it depends on the interaction between the surfaces, it depends on two things. It depends on the properties of the mass. What's it made out of? Depends on the properties of the surface. What's it made out of? It depends on the smoothness of each surface. It also depends on anything that's on the surface. And so all these properties come together to make it so you can't just say, for example, that one type of material on another type of material is always going to be the same mu sub s. It depends on several different factors. Even your tires, the tire compound is going to give you a different amount of friction on asphalt versus concrete. And it'll give you different amount of friction on smooth concrete than it does on rough concrete. And so there's many different factors that affect it. Put water on the road and that changes the friction. And so there's many factors that go into this. So the coefficient of friction here is a unique sort of thing to a particular environment and particular situation. And so it's not something that's very easy to calculate ahead of time. And so this is just something that we typically experimentally measure. So in a problem, you'll just be given the number or you have to figure it out.